So this time, integral from 1 to infinity, 1 over x dx. So very similar to the last one. Okay, we can start by introducing our parameter. We can go from 1 to t. Now we have a definite integral. We're also going to set up the limit as t approaches infinity. And for this one, it may not seem different than the last one we went through, but now the antiderivative of 1 over x is going to be ln absolute value of x from 1 to t. So we finish off our FDC2, plug it in, we get ln of t minus ln of 1. Now, ln of 1 we know is just going to be 0, and so really we have just the limit here as t goes to infinity of ln of t. Now, this is one that often people do mess up, but ln of t, this is going to be approaching ln of an ever increasing number, and so it itself is going to be ever increasing. Okay? Now, what that means for this one is that this area is not 1. This area is not even finite. This area is in fact going to be ever increasing. Now, this is what I want to talk about. We have these two different integrals, we have these two different functions. One of them is 1 over x, and the other one was 1 over x squared. Why do we have this drastically different behavior between the two? Well, before, when we were talking about functions going to 0 fast enough, we said that 1 over x squared did approach 0 fast enough. Here, when I look at 1 over x, let's take a look at this new function. We have 1 over x, and we would like to look at the area underneath that. Well, right away, there is a huge difference between the two functions. Okay, if I am focusing here on the dark region, okay, the area underneath 1 over x compared to the area underneath 1 over x squared, you'll notice that 1 over x squared does approach 0 much faster than 1 over x. And as x increases and increases, you'll notice that 1 over x actually approaches 0 very slowly, especially compared to 1 over x squared. And so the area underneath 1 over x, you would expect to be much larger than the area underneath 1 over x squared. And in fact, as we've shown here in the two integrals that we've done, the area underneath 1 over x never stops increasing. It is an infinite integral. And the area underneath 1 over x squared, there's no issue. It is equal to 1. So we are going to spend some more time talking about that in the next section. Specifically when we go through p integrals. But for now, let's do a couple more examples looking at this type 1 improper integral, and also let's define how to actually deal with them. Okay, so let's actually define then the first type of improper integral. So we start off, if we have a function f of x that is continuous, on the interval starting at a going all the way to infinity, then how can we deal with an improper integral from a to infinity of f? Well, we introduce our parameter. We know that we can do the integral from a to t because our function will be continuous on that interval. And then we're going to take the limit as t approaches infinity. And that's the first thing. Now, we know we're dealing with limits. On the right-hand side, we have to do the limit at the end as t approaches infinity. We also know that limits don't always exist. And so we have further definition, is that we say the improper integral either converges if the limit exists, and 2, we would say that it diverges if the limit does not exist. Okay, and really when we're looking here for a divergent integral, we'd be looking for that limit likely to be infinite. Okay, and so here this is sort of the first time that we are introduced to these concepts of convergent integrals or divergent integrals. And this is going to be a big part of the course moving forward, not only with improper integrals, but definitely later on when we take a look at infinite series, we're going to be very interested in when those series converge and when they diverge. Okay, so actually looking back, we did these two examples. And we know that in the first example, we have that the limit here was 1, and so we can say that this one definitely converges. Okay, and in our second integral, we have that the limit was infinite. Okay, and we also know that an infinite limit like this does not exist, and so this second one was divergent. So we can add that in. Integral 1 to infinity 1 over x squared converges, and integral 1 to infinity 1 over x diverges.